This lecture is going to be about the substitution in multiple integrals. And the good news is we have seen this kind of technique before in Cal 1. So let's take a look here. Right here, substitution for the single integrals. As you can recall, in Cal 1 we work with single variable function. So let's have an example of that right here. fx. Okay, and with this just one variable, we are going to assign this function to be equal to 2x plus 1 to the power of 5. Okay, and we want to perform an integration on this function. And it should look something like this. Single integral. One integration sign of this function, and that is 2x plus 1. And we want to perform the integration with respect to the only variable that we have, and that is x. So here we have this, I forgot the power of 5 right here. And this is going to be dx differential x. And let's also make this integral a definite one. So let's assign the boundaries for x. X starts at 0 and ends at, okay, let's make it 1. Now we want to evaluate this integral. And one way to do that is to perform the multiplication 5 times. We need to work on this factor, right? 5 times, multiply them in. And we are going to get all these terms, and then in the end we can perform the integration on each one of them separately. That can be done, but some of you might think that that is too long to perform the multiplication 5 times. It's going to take a lot of time to finish that. So some of you might say that there must be a better way. So one way to do this is to simplify the function that we have right here, fx, into something that is simpler. So we are going to simplify. First step is to simplify this function that we have, okay, into something else. So what about we assign the inside of this parenthesis into just one variable? So let's make the inside of this parenthesis to be equal to just u. Okay, so u equal to 2x plus 1. With this, we are going to get this new expression of u to the power of 5. Okay, so this is a new function, but as you can see, this new function is in terms of u only. There is no more x. So this new function has to be expressed as a new function of u, d of u, equal to u to the power of 5. Now that is the first step that we did in order to make this integral a little bit easier to manage. So that is number 1, to simplify the function that we have into something simpler. So with this, you can make a note that this looks simpler than what we had before, and this should be easier to integrate. Okay, so with this, we are going to put this gu equal to u to the power of 5 into the integral. Okay, so that is the idea of substitution, right? Put this back in. So here is going to be equal to this integration sign, and this is changed to u to the power of 5. Okay, and at this point everything else is still the same. We still have this dx, and we still have this x equal to 0 and x equal to 1, because what we just did is to just work on this term only, nothing else. We didn't touch anything else. But when you see an integral like this, it's going to be a problem, right? How are we supposed to integrate u to the power of 5 with respect to x? It doesn't make sense. So we are going to have to do something with this dx right here. And not just dx, we need to do something with this boundaries, x equal to 0 and also this one. So let's start with this dx. We have to change it to be in something else in terms of u. So that is number 2 that we are supposed to do. So number 2 right here, we are going to transform dx into du. Of course, the new one is u, right? So this second step is about transforming dx into du. So we want dx to be expressed in terms of u. Okay, and we can do that by using the expression that we have right here, u equal to 2x plus 1. So let's work on that. So I'm going to work right here. Okay, so we have this u equal to 2x plus 1, and we can differentiate this u with respect to x. So we have du by dx equal to 2. And with this, you can move things around and you get this dx equal to du over 2. And there you go, we have this expression, and we can put this back into the integral. Dx equal to du over 2. We have transformed dx into du. So this can be gone, and we can use the new one. Du over 2. Alright, differential u over 2. Now, next thing we are supposed to do is to work on the boundaries. So number 3 that we are supposed to do in order to change the whole thing, to complete the substitution technique. Number 3 is to translate. Okay. Translate the boundaries. Okay, we are talking about x equal to 0. So this is the first one that we have, x equal to 0, and the second one is x equal to 1. So we need to translate this. Okay. Now, x equal to 0, we can just put that into this expression right here, u equal to 2x plus 1. This, x equal to 0, then u is going to be equal to 1. So we have this u equal to 1 for the lower bound of u. Now, x equal to 1, once again, put it into here. X equal to 1, then we have u equal to 2 plus 1, and that is 3. So u equal to 3, that is the upper bound for u. So let's put these back into the integral. So this is going to go away, and same with that. Okay, now we have u equal to 1 right here, lower bound, and u equal to 3, upper bound. Now we can just proceed with this integration normally. So this is going to be u to the power of 6 over 6 times 2, that's 12, and we are supposed to evaluate this at u equal to 1 and 3, and in the end it's going to come out to be equal to 182 over 3. I worked on this for you already, but you can check about the correctness of this number. Okay, so that's how you perform the substitution technique in single integral. Now we are going to extend this idea to multiple integrals, and it's going to be similar but quite a bit more challenging. So let's take a look here. So now we are going to move to multiple integrals, but it's going to be substitution again. When we talk about multiple integrals, we have two types, right? Double integrals and triple integrals. So let's make a note right here that you are aware that this can be applied to both double and triple. But let's start with the easier one. We are going to start with the double integrals, and we are going to try to perform this technique, substitution. So let's start with the expression of the double integral. So let's have one right here, double integration sign with multivariable function f. And this function right here needs to have more than one variable. Now let's stick with the Cartesian coordinate to keep it simple. So we are going to use x and y as our variables for this function. And then we want to perform the integration of this function with respect to the differential area, dA, over an integration domain R. This is old stuff, right? We learned about this maybe 3 to 4 lectures back. Now let's take a look at the function that we have right here, function of x and y. As you can see, this function is expressed in terms of x and y variable. So in order for us to proceed with the calculation of this integral, we need to express dA in terms of x and y too. Otherwise, we just don't know how to do with all the terms we have in the function, right? So this dA cannot stay as dA. It has to be expressed in terms of x and y. And by now we know that this dA is equal to either dx dy or dy dx, either one of them. You can pick either one because in the end, dx dy or dy dx is the same area of a tiny rectangular piece inside the integration domain R. So pick either one. Which one to go for, that depends on the situation you have. Alright, now that is good. dA can be expressed in terms of dx and in terms of x and y, no problem. Now that is not enough. We have to do the same for the integration domain R too. So the boundaries are supposed to be expressed in terms of the variables that we have. R right here has to be expressed in terms of x and y. And there you go, we have the complete general form of the double integral in Cartesian. And we want to evaluate this. We want to find the answer for this. One way to solve this is to work on this directly, straightforward, working on x and y as it is. And that's what we did in the previous chapter. We worked on this x and y, we didn't change anything. But today we are going to try something a little bit different, which is the substitution technique. For example, let's take a look up here. We see this function up here, 2x plus 1 to the power of 5, and we think this is too complex. I don't want to work on this directly. I want to change it into something simpler. That is the idea of substitution. And we are going to do the same with this function down here, multivariable function f of xy. For some cases, you think it's too complex. So let's try to change it into something simpler. And we are going to follow the same guideline that we had before for the single integral. Simplify the function, transform the differential, and translate the boundaries. It's going to be quite similar, but a little bit different. So let's take a look at how it's done right here. Number 1, we are going to simplify the function, the one that we are not happy with. So number 1, simplify. Simplify f of xy that we think is too complicated. We are going to change it into something simpler. And we are going to call that new function g. G right here is supposed to be simpler than f. Okay. Let me write it right here. Supposed to be simpler. And that's why we change it, right? If we change it and it becomes more complicated, then there is no point to do that. So we have this g and it's supposed to be easier. But let's take a look at the variables of g. So let's take a look at the number 1 up here for the single integral. We were working with x for f, right? But in the end, we have this new variable u for g. And this u comes from the substitution that we created. So it's going to be the same thing for this f of xy. We start with x, but in the end, this x is going to get changed, substituted into a new variable, and we are going to call that u. Okay, that is the first one. But then this f has another variable y. So same thing is going to happen. Y is going to get changed, transformed into another form, another variable. And we are going to call that new variable v. So there you go. You start with 2 variables, x and y, the original ones, and then you end up with 2 new ones, u and v. Okay, so there you go. That is the idea of simplifying the multivariable function f of xy. Now we are going to move to guideline number 2, step 2. That is transforming the differentials. So put 2 right here. Transform. Okay. So transform what? We have this differentials right here, dx dy or dy dx. Okay, so let's assume that we have dx dy, and it's okay to have dy dx too, or dy dx. Okay, and we cannot stay with x and y because we have moved to the new variables, u and v. So this has to be changed into a new differentials too in terms of the new variables. So instead of dx dy, we are supposed to work on du and dv instead. And of course, or dv du. As you know, the order of the differentials can be swapped or interchanged. So there you go. We have to move from dx dy to du dv, but it turns out that this process is a little bit challenging. You cannot go directly from dx dy to du dv because the relation between them is not always directly equal to each other. So let me give you a formula to connect them together, to connect dx dy to du dv, and it's going to be this one. So if you have dx dy and then you want to change it to du dv, it's going to follow this formula. it's going to be equal to some factor at the front right here. I'm not going to give this to you right away. And this factor is going to get multiplied with du dv. That's it. That is the formula to connect them together. So no surprise with the du dv, right? It has to be there. But what is missing is this factor, unknown factor. And I'm going to give this to you. This unknown factor is the determinant of the Jacobian matrix. This might sound new to you. Don't worry about that. Determinant of the Jacobian matrix. So let's make a box around this formula. Okay? Now, in order to change from dx dy, the key is this factor right here, Jacobian determinant. Now, let's take a look at the details of this formula on the right-hand side. Okay, let's split the screen right here. And we are going to bring this formula right here again, dx dy, okay, equal to, all right, this Jacobian determinant, or you can call it the determinant of the Jacobian matrix, times du dv. Okay, du dv, and let's make a box around that again. Okay. Now let's start with the Jacobian matrix, what that is. So let's have a definition for that. First of all, J right here is the Jacobian matrix. Jacobian matrix. And for those of you who don't know what this matrix is, I'm going to give you this definition. I try to make it simple. So Jacobian matrix is the first order derivative of a vector function. So let's write down that. Jacobian matrix is the first order derivative of vector function. Nothing hard about the first order derivative, right? But this time around it's going to be applied to vector function. A little bit different from what we had before. So let's take a look at an example of a vector function. So I'm going to construct one from the relation between the original variables x, y, and the new variables uv. So at this point I'm going to construct a vector function connecting x, y to uv. So this connecting, let me change this to x, y. Okay, start with x, y, and I'm going to change this into uv. And I'm going to use this relation to build the vector function. So let's start with the first one. I'm going to express the old variable x as a function of the new variable. As a function of the new variable, u and v, we have two of them. And I'm going to call this first function because we have one more. And I need to do the same for the y variable. Express the old variable in terms of a function of the new variable. Function f2 of the new variable, u and v. So there you go. Right now we have two variables. Old ones, x, y, and we have two functions f1 and f2 on both sides of the equation. And we have two equations. But when you have something like this, two equations to work with, it's a little bit more complicated. What about we try to simplify this again? Combine these two equations into just one equation. I don't want these two. I just want it to be just one equation so that it's easier to do some calculation on them. But if I do this, I need to group them together. I need to group x and y right here into a vector. Alright? Okay, so that is a vector with x and y as its element. And on the right hand side, same thing. It's going to be a vector of two functions. So there you go. Right now we have this one equation right here, and what you see right here is an example of a vector function. So you can, what about, I can make this a little bit bigger. So let me change this. Well, that's okay. So make a note right here that what you see on this xy equal to f1, f2 right here is an example of vector function. This is vector function. Okay, how is it going to work? Why is it a vector? Let's take a look here. You can see that the input for this function is u and v. U and v, right? So we have this as an input, vector of u and v. And then this vector got transformed through this function f1, f2. f1, f2, and in the end, we get this vector of x and y. So in the end, we get this vector of x and y. And that's how the function works. It's like a transformation. We have this as input, one vector, and output as another vector. So there you go. Now we have the vector function. Now we want to find the Jacobian matrix of this vector function. So let's take a look at the definition again. Definition is the first order derivative of this vector function. So we have to take care of these two functions. We need to find the first order derivative of these two with respect to all the variables that we have. So let's take a look at the result right here. Jacobian matrix is going to be equal to the first order derivative of the first function, df1, with respect to the first variable u. But as you can see here, we also have v to worry about. So we can't just leave it alone. We have to perform the same calculation with respect to v2. So first order derivative of the same function with respect to another variable. And there you go. That is the second element in this matrix. Now we are done with the f1. We have to do the same for f2 because f2 is inside this vector function. So df2, first order derivative of f2 with respect to u. And okay, let me fix on this. I want this to be more clear. D of f2. Okay, d of f2 with respect to the first variable, u. And now d of f2 with respect to the second variable, v. So there you go, that is it. The Jacobian matrix. First order derivative of all the functions we have with respect to all the variables that we have. Okay, let me write that down. First order derivative of all the functions that we have, of all functions with respect to all variables that we have. That's it. And what you see right here, we have 2 by 2 matrix. So in this case, we have 2 by 2 for 2 variables. Okay, so with this, make a note that this is 2 by 2. Okay, now that you have found the Jacobian matrix, in order to fit this into the formula that we had before, all you need to do is to find the determinant of this matrix. And I'm pretty sure that you guys know how to do that. So let me adjust this. It's supposed to be a little bit longer. Okay, now that you know how to find this Jacobian matrix, and then later on find the determinant of this, you can put this result into the formula and you can transform dx dy into du dv. Okay, now let's move to the last step that we need, which is to translate the boundaries. Okay, so last one is the translate. Okay, translate the boundary. That right now we have this integration domain in terms of x and y, but we cannot stay with x and y variable any longer. So we need to change it into a new one in terms of u and v. Change this r of xy into a new r. Okay, in terms of u and v, and that way you can use it to evaluate the integrals. Okay, so that is it. As long as you know how to simplify your function to make it simpler, as long as you understand this process of this formula, how to find the Jacobian matrix and how to find the determinant of that, and in the end you translate the boundaries, you are in good shape. Now the question is, what about we want to work on triple integrals? How is it going to affect the formula and the guideline that we have right here? So I'm going to add more elements into the contents that we have right here. So this is going to be for triple integrals. First of all, when it comes to triple integrals, we are going to work on a function with 3 variables. So you are going to start with this f of x, y, and z. And once again, for this substitution, you are not happy with this f. Too complex, and we want to change it into something else, something simpler. Same thing. This f is going to get changed into g. But instead of having u and v, just 2, right now we need 3, right? So just like before, we add one more. It's going to be w. You can pick something else, but usually we use the u, v, w. So that is the first step, simplify it. Okay, this is to simplify. Now, how is it going to affect the formula in terms of the transformation of the differential? Okay, this is going to happen. So we are going to include the new variable dz right here. Okay, this one is for the triple integral, and it's going to be the same for the du dv. We are going to have this dw for the case of triple integral. Now, what's going to happen to the vector function? Of course, we are going to have this extra term, right? Z, x, y, and z. So your vector is going to get longer, right? 3 by 1. And all of these old variables, original variables, x, y, z, has to be expressed as a function of the new variables, which means that f1 right here, not just uv and w, not just uv, we also have w inside this function f1 too. Same with f2, w in there too. And last one, z has to be expressed as a function of the new variable. So we have this f3, u, v, w, and this vector gets extended to include the extra term. Alright, now vector function gets one more dimension, and of course this is going to affect the Jacobian matrix. Alright, let's take a look here. Now that we have one more variable, w, to consider, it means that the f1 right here, we need to find the first order derivative of that with respect to another variable, w. Okay, same thing with f2 with respect to w. And since we have f3, we need to add that df3 with respect to the first variable u, df3 with respect to the second variable v, and last one df3 with respect to w. And there you go, we have this bigger Jacobian matrix, 3 by 3. And this one is for triple. Okay, and this one, 2 by 2, that's for double. So there you go. In the end, it's the same pattern for this formula, going from differential of the old variable to the differentials of the new variables. So you can add this right here. If you have one more variable, you can add dz, and this one you can have dw. Okay, now the last one, the translation of the integration domain. Same thing. For the triple integral, we are going to have integration domain, and we call it d, right? D of x, y, and z. Of course, we cannot stay with x, y, and z. We need to move to u, v, and w. So you have to find a way to change it to d of u, v, and w. And that's what you need to do. Alright, so we have covered the substitution for both double integrals and the triple integrals. Now let's move to some examples in the next slides. Here we have example number 13, which is wrong order. So why don't you change this 13 to 6? Right, this is supposed to be example number 6. In this example, we are supposed to try the new technique that we just learned, the sub technique, to evaluate a double integral. So let's take a look at the double integral that we have right here in this problem. So we have 2x minus y over 2 and that is the multi-variable function that we are supposed to work on. So let's write down that function right here. The function that we are supposed to work on is f of xy, right, to Cartesian variable xy equal to 2x minus y over 2. Alright, that is the function. Now let's take a look at this dx dy. Of course, this one is differential area, dA expressed in terms of x and y. So this one is dA. And we are going to use sub technique to solve this. But before that, I need to make it clear to you that for this particular problem, we don't need to use this technique at all, right? And the reason for that is because when you look at this function right here, f equal to 2x minus y divided by 2, what you look at here is already easy to solve, right? You can integrate this with respect to x or y quite easily. But we just want to try out our new technique today. So let's just assume that we are not happy with this f right here. Even though it's already easy, we want this to be even easier. Alright, so that is the assumption that we have. We want to make this easier. So we are going to simplify this f into something simpler. Alright, so how to make this simpler? What about I make the whole term right here, 2x minus y divided by 2 to be equal to u. Alright, instead of having a fraction, I just have one variable. That's definitely easier. So that is the first sub. U equal to 2x minus y divided by 2, first sub. And with this u, I can declare the new function in terms of u and v. So the new simpler function, I'm going to call it g again. And this g, since I am working with two variables, of course I need to have two variables in here, new ones, u and v. And for this case, this g is going to be equal to just u from here. Okay, so there you go. As you can see, we start with the two original variables x and y, and after the transformation we have to move to new variables u and v. And as you can see here, we have only used u when it comes to sub, right? But what about v? We haven't used it yet. So let's find a place to use v, and in order to further simplify the double integral that we have. So let's take a look at this double integral. And I see this place right here that I can use v to make it more simple. So what about I declare this to be equal to v? Okay, that is the second sub. And v is going to be equal to y over 2. So there you go. Right now I have two subs, and they show the relation between the old variables. Well, what about I change to original variables to the new variables? Okay? So, first step is to simplify the function that is already easy to be even easier. So that is right here. Simplify, and that is the first guideline, right? First step in the guideline. Simplify the function. Okay, so we are done with that. So we have this new simpler function, g of uv equal to u. Now the next thing we are going to do is to transform the differentials from the original variable dx dy into the differentials of the new variables du dv. So we need to rely on this one formula that I showed to you. Dx dy equal to the Jacobian determinant, or you can call the determinant of the Jacobian matrix, times du dv. And we are going to use this to transform the differentials from the original ones to the new ones. So just one formula that we need right here. Okay, so there's nothing to do with du and dv. What we need to do is just find this Jacobian and find the determinant of that. So in order to find the Jacobian, once again, Jacobian is the first order derivative of a vector function. So first of all, you need to construct the vector function from the relation between the original variables and the new variables. And we are going to use these two subs to find the vector function. So once again, just like what we did in the guideline, we are going to have this vector of the original variables x and y, and we are going to show this express these two variables as a function of the new variables. So first one, x expressed as a function of the new variable, we call that f1 of u and v. Okay, and same for the y variable, y expressed as the function of u and v, and we call this f2. Now our job is to find f1 and f2. Okay, and we are going to have to use the substitution that we have up here in order to find this expression. So we need to make x alone, x and y alone on the left hand side. So what about I separate this right here? So looking at this, I move things around and I get this x equal to u plus y over 2. Just move things around. And looking at this, v equal to y over 2. So I know that this one, y over 2, is equal to v. So in the end, I have this x alone on the left hand side equal to u plus v. And there you go. I express x as a function of the new variables, u and v. So I have got f1 right here. f1, x equal to u plus v. Now I need to work on f2. So looking at this, v equal to y over 2, I just move 2 up and I get this y alone on one side, and it's equal to 2v. And there you go, y expressed as a function of the new variables, y equal to 2v. So there you go, we have the vector function. Okay, vector function from two subs that we have. Okay, now that we have the vector function, we are ready to find the Jacobian matrix. And as you know, Jacobian matrix is the first order derivative of this vector function with respect to all the variables. So let's put the formula right here. Okay, the form, we diff the first function f1 with respect to the first variable u. And of course we have v2, we have to do the same thing, and that is the second element. Diff f1 with respect to v. And since we have f2, we do the same thing. df2 with respect to u, df2 with respect to v. And that is it, the Jacobian of this vector function. And let's find out about that. So we are going to start with f1 right here. df1 with respect to u. f1 is this, u plus v. We need to diff this u plus v with respect to u. Diff this with respect to u. Of course, we get just 1 out of that. So let me write down right here. First element is just 1 from the partial diff. Okay, this doesn't look nice. Let me change this to 1. Now, next one, diff f1 with respect to v. Same thing. I diff this same function with respect to v, and I also get 1 out of that. Okay, now move to third element. Diff f2 with respect to u. So I have to move to this and diff this with respect to u. Since there is no u here, I get 0 out of that. So there you go, third element. Now move to the last element. Diff f2 with respect to v. Diff this with respect to v. Of course, I get 2. So there you go, we have got the Jacobian matrix. But in order to use the formula, we need to find the determinant of this Jacobian matrix. So from this, we can find the determinant of Jacobian matrix. And it's going to be equal to 1 times 2 minus 0 times 1. So in the end, we have this determinant to be equal to 2. Alright, so which means that the relation between dx dy is going to be this, dx dy equal to 2, the factor that we just found, times du dv. Alright, so the transformation of the differential is done. Alright, so dx dy equal to 2 du dv. Now the last step that we are supposed to do is to translate the boundaries, the integration domain. So we are going to look at all the boundaries that we have. So let's start with the first one, the lower bound of the x variable. We have x equal to y over 2 as the lower bound, right? And then we also have the upper bound for x, and that is x equal, right? Let me move this up a little bit. X equal to y over 2 plus 1. Okay, two bounds for x variable, and then we also have two bounds for the y variable. So let's work it over here. Y lower bound equal to 0. Upper bound for y equal to 4. And our job is to translate all these boundaries into u and v. Okay, we want to make this happen. Change this to u and v. Alright, now let's work on the first one. So this one, let's work on this equation. X equal to y over 2. So x equal to u plus v. So go to here, x equal to u plus v, right? So I'm going to put u plus v over here. U plus v equal to x equal to the other side of the equation. We have y over 2, and y over 2 right here equal to v. So this is equal to v. Cancel this and this. We have u equal to 0 as the first boundary in terms of u and v. At this point, we don't know whether this is a lower bound or the upper bound. We have to look at the whole picture. We have to look at all the boundaries to determine whether this is low or high. Okay, so let's move to the next one. This one, x equal to y over 2 plus 1. Okay, move to here. X equal to u plus v. Once again, we have this u plus v on the left hand side. Now on the right hand side, y over 2. Of course, this is equal to v again, but this time we have plus 1 over here. So cancel this with this. We have u equal to 1. So at this point, it becomes clear that the lower bound of u is equal to 0 and the upper bound is equal to 1. So low bound of u. This is high bound of u. Okay, that is good. Now let's move to the bounds for the y variable. So here we have y equal to 0. And from the sub, we have this y equal to 2v. So let's use that. Y equal to 2v. So 2v equal to 0. So in the end, we have this v equal to 0. We don't know whether this high or low. Let's wait. Now let's work on this one. Y equal to 4 and y equal to 2v equal to 4. So in the end, we have this v equal to 2. At this point, it becomes also clear that v equal to 0. This is low bound. Low bound of v, and this one is the high bound of v. So combining all of this, we know that u. So we know that u is supposed to be in between two values, two constant values, 0 and 1. Alright, that is the range for u variable. What about v? V is supposed to be between two constant as well. V less than 2, greater than or equal to 0. So there you go, we have got everything. Oh, by the way, this is the third step, translating the boundaries. So start with the simplifying the function, number 1. Perform the transformation of the differentials, and we have done that right here. And last one is the translating of the boundaries, and we have got that as well. So with all these information, we can move to the next slide to solve this double integral and use this sub technique. Okay, so before anything, let me write down all the information that we got again. Okay, so from 1, we know that this new function is going to be gu of v. What about I use blue? I like that better. So g of u and v equal to, okay, just u. We have found that. And number 2, the transformation of the differentials. We have found that du dx is equal to 2d, oh, I'm sorry, dx dy dx dy, okay, dx dy equal to 2 du dv, and 2 comes from the Jacobian determinant. Alright, and last one is the boundaries, the new ones, in terms of the new variables. And we have this u, okay, u between 1 and 0, and v between 2 and 0. So if we put everything into a graph, what we just did is to simplify the integration domain. Working with x and y variable, integration domain would look something like this, a parallelogram. But with the sub technique, we have simplified it into a rectangle. So once we simplify this function of x and y and integration domain, we are going to get a new integration domain on the u and v axis. So in the space of u and v right here, we are going to get a simpler integration domain. And as you can see, u has to be between, very simple, u between 0 and 1, and v between 0 and 2. So there you go, we have a rectangle integration domain. Okay, so let's continue. Let me mute my cell phone. Okay, hold on. Alright, I'm ready. So we have transformed the integration domain into something simpler, and we also have the simpler function as well. So with this top surface, it becomes also simpler. So with these information, we are going to perform the integration, double integrals, on u and v variables. So let's start with the original double integrals. So the original, we have this. So we have, let me check. Okay, I have it right here. So we have this 2x minus y over 2, right? And we have this dx dy. And x starts at y over 2 and ends at y over 2 plus 1. Okay, this is from the problem. And y starts at 0 and ends at 4. Okay, now we want to change everything into u and v. So let's start with this. 2x minus y over 2, it's going to be this new one, u. So this new double integral is going to be just u. Now we are going to change this dx dy into the new ones, and that's equal to 2 du dv. So it's going to show up right here, times 2 du dv. Okay, now the lower bound, and as you can see here, we have the order of the integration here, du and then dv. So the inside integration sign is going to be for the u variable, and as you can see, u has to be in between 0 and 1. So we can put this into the integral sign, u between 0 and 1. And now for v between 0 and 2. So v between 0 and 2. From this point on, you can just integrate this normally, like you are working with x and y. Instead, you just work on u and v. Okay, so let's split the screen right here. So we are going to integrate this to u, okay, with respect to u. Let's start with du first. Integrate this with respect to u. It's going to be equal to, alright, equal to u squared over 2, okay, times 2. And this is going to cancel with this right here. And we are supposed to evaluate this at two values of u equal to 0 and u equal to 1. And don't forget to integrate this one more time with respect to v. Alright, v starts at 0 and ends at 2. So from the inside of this integral, we have this 1 goes in. Alright, this becomes just 1, and 0 goes in. This becomes 0. So in the end, we have this integration of 1 minus 0, which is just 1. With respect to v, starting from v equal to 0 and ends at 2. Easy, right? So in the end, we have this v evaluated at 0 and 2, and we get this 2 as the answer for this example. So if you want to know what happens, a few things happen. First of all, we change the shape of the integration domain into something simpler. And we also change the shape of the top surface into something simpler too. At this point, the top surface of our object is going to be just u. Okay? But in the end, the answer is 2. You can choose to work on this double integral using x and y variable, and in the end, the value is supposed to come out to be equal to 2 as well.